All right, we have one more type of transformation that we have to look at, or one more pair, I guess, of transformations that we have to look at. Let's do this just like the other ones via an example. Let's sketch graphs of f of x equals x squared, because I know you missed that good old parabola, and g of x equals the quantity 2x squared. Now, we have graphed f of x equals x squared so many times that if you don't know what it looks like by now, I don't know if I can help you. Unless you've skipped lots of videos and this is the first time you're seeing it. But we have drawn this parabola so many times. So let's do it once more. And now let's make a table of values for our graph of g of x. So we're going to pick different values here than we've done before, which might seem a little weird, but you'll see why in just a moment. Let's take a look at 1.5, 1, 0.50, and then the negative versions of these numbers. And we're going to do these one at a time, starting with 1.5. If we plug in 1.5, this is going to be 2 times 1.5 squared. 2 times 1.5 is 3. And 3 squared gives us 9. All right, then we look at 1. Well, when we plug in 1, that gives us 2 times 1, quantity squared. 2 times 1 is 2, and 2 squared is 4. Now, when we plug in 0.5, we've got 2 times 0.5 squared. 2 times a half is just 1. And 1 squared is 1. When x is 0, we've got 2 times 0 squared. 2 times 0 is 0. 0 squared is 0. When we've got negative 0.5, it's going to be 2 times negative 0.5 quantity squared. 2 times negative 0.5 is negative 1. And negative 1 squared is positive 1. In fact, in all of these, we're going to see the same values that you saw here, because when you square a negative, you get a positive. So we're going to have 1, and then 4, and then 9. All right, so let's take a look at these points. We've got 1.5 comma 9. It's going to be right about there. We've got 1 comma 4, it's going to be here. 0.5 comma 1, 0, 0. Negative 0.5, 1, negative 1, 4, and negative 1.59. And we're going to have a parabola again, but this parabola is going to be skinnier. What has happened to each of these points is they've moved closer to the y-axis. And so what we've really done here is we have shrunk this horizontally. Everything is moving inwards closer and closer to the y-axis. So effectively, we have shrunk the graph here. And we have shrunk the graph by a factor of 1/2. Everything is 1/2 as far away from the y-axis that it was before. So this is a horizontal shrink by a factor of 1/2. This is probably not what we expected. we might have expected when we're multiplying something by 2, that's actually stretching it. That's what happened when we were looking at vertical stretches and shrinks. However, when we are looking at horizontal stretches and shrinks, if we're multiplying by something larger than 1, we're going to be shrinking, and if it's smaller than 1, if it's between 0 and 1, that's when we end up stretching, and that's going to be the rule. To sketch the graph of y equals cx, if c is greater than 1, like it was here, shrink the graph of y equals f of x horizontally by a factor of 1 over c. So in this case, c was 2, and so we shrunk by a factor of 1/2. If c is between 0 and 1, though, stretch the graph horizontally by a factor of 1 over c. And that's exactly what we're going to do when we look at the graph of the function h of x equals 1/4 x quantity squared. So here we're multiplying the inside of the function by 1/4. So c is 1/4, and that's between 0 and 1. So we're going to stretch the graph horizontally by a factor of 1 over c. Well, 1 over 1/4 is the same as 1 times 4 over 1, or 4. So we're going to be stretching the graph horizontally by a factor of 4. So any point that we have on the original graph will move 4 times as far away from the x-axis, from the y-axis, from the y-axis. So this point is 1 unit to the right of the y-axis. If we stretch it by a factor of 4, it's going to have to be 4 units to the right of the x-axis. That's going to be right here. If we look at this point, it's 2 units to the right of the x-axis. If we stretch that by a factor of 4, it needs to be 8 units to the right. So 1, 2, 3, 4, 5, 6, 7, 8. It's going to go right there. Let's see. Nice. And then this point all the way up here is 3 units to the right of the y-axis. If we stretch this by a factor of 4, it's going to be 12 units to the right of the y-axis. And that is going to put it right here. And the same thing is going to be true for these 3 points, except on the left-hand side. So we've got a point that is 4 units to the left. We've got a point that's 8 units to the left. And we've got a point that's 12 units to the left. And then, of course, the origin stays where it is. And we end up with another parabola. But this one is stretched out very wide horizontally. And so this is the graph of h of x equals 1/4 x quantity squared. Whenever we're taking something and stretching or shrinking it horizontally, we are moving the points closer or further to the y-axis, depending on whether we are stretching or shrinking. Really quickly, just another example of a horizontal stretch. If we were to take a circle, and again, this is not a function, I just want to talk about stretching things, and we were to stretch this out horizontally by a factor of 4, then the end points, which are 2 units away from the y-axis, get stretched 4 times as far, so they're going to be 8 units away. So 1, 2, 3, 4, 5, 6, 7, 8. So it's going to be there. And then this other point on the left is going to be 8 units to the left. The top and bottom are going to stay where they are, because if we're stretching something about the y-axis, anything that's on the y-axis is going to stay there. And then we end up stretching this circle into an oval shape that ends up being much, much wider than the original graph. And so it looks something like that. It gets stretched out much further away from the y-axis. And there we go.